Okay, today we'll look at a different method of approximation. It goes Ramsell, Kramer's, Lewin. Okay, so instead of writing all these three names all the time, we just say this is the WKB approximation. Okay, it's a nice, powerful method to obtain approximations to the time-independent Schrödinger equation. Okay, so what we are after is we are trying to find what psi of x is. Psi of x is some function which obeys the Schrödinger equation, and especially if we are looking at the eigenfunctions of the Schrödinger equation, then we are trying to obtain approximation to the eigenfunctions. Now remember that this is a complex function. What we do is we write this as a of x plus, not plus, times e to the I phi of x. Okay, so any complex number you can write as a magnitude and a phase, right? So it will be a function of x, obviously. And a and phi are real numbers, okay? So what we need to do now is put this into our Schrödinger equation, h bar squared over 2m d squared dx squared. Okay, psi of x is equal to e minus v of x, so I'll move the potential to the right, times psi of x. Okay, and I'll substitute this in psi x. Okay, so I'll need the second derivative of that. So let's just do that algebra. So psi prime is going to be, okay, a prime times e to the phi x plus a times I phi prime, right, derivative, e to the I phi. Okay, so that's the first derivative. Now we have to evaluate a second derivative. Psi second derivative is equal to, okay, the derivative of this stuff. So it's going to be a double prime plus I. Derivative of this is a prime phi prime plus I a phi double prime, right? So it's just the derivative of this parenthesis. And then I have to add to that this thing times the derivative of e to the I phi. So I'm going to add to this plus I phi prime, derivative of this, okay, times, okay, this full term a prime plus I a phi prime, okay, everything multiplied by e to the I phi. Okay, please check my algebra. Okay, so let me just squeeze in one more line here. This is going to be equal to, let me write the real stuff and the imaginary stuff together. Okay, so I'm going to get a double prime, right? And then these are all imaginary. Then there's here a minus, what? Minus a phi prime squared, right? Those are the real terms. And then I have the imaginary terms, which is going to be, okay, a prime phi prime. There are two of them, 2i a prime phi prime. And then I also have an I okay, where's my other I? It's over here, right? I a phi double prime, everything multiplied by e to the I phi. Okay, please check my algebra. So now let's put that into our Schrödinger equation. So we are going to get minus h bar squared over 2m. This whole thing, okay, the a double prime, so let me just write it one more time, a phi prime squared plus 2I a prime phi prime plus I a phi double prime. Okay, e to the I phi. So that's just the second derivative term. Then I have that thing is equal to e minus v of x times a e to the I phi. Okay, so I can just cancel the e to the I phi's. All right, I have something like this. Okay, so I have split the equation into real and imaginary parts. And I have one equation for the real part, another equation for the imaginary part. So let's just write those things down. Let me multiply by the reciprocal of this, okay? So that I'm going to get a double prime minus a, okay? I'm just going to write the real pieces, phi prime squared is going to be equal to minus 2m e minus v over h bar squared a. All right? So that's just for the real part, okay? The real part on the left equals real part on the right. There's no imaginary part on the right, so the imaginary part on the left must add up to 0. A prime, phi prime, plus a phi prime is equal to 0. Okay, so all I have done, okay, so I have not done any approximations or anything yet. All I have done is that I have just split up the real and imaginary parts of the equation. Now I have, instead of psi, which was our complex variable, we now have two variables, a and phi, which are both real, and two variables, two equations. So this is equivalent to the Schrödinger equation, but as you can see, this is not an easy equation. There's a phi prime squared here, multiplied by a, so these are functions. A is a function, phi prime is a function. Yes? Phi, which one? Second one, thank you. So I have these things multiplying one another, so it's a very nonlinear equation. Okay, so it's not in no ways any easier to solve. Okay, so the WKB approximation that we are going to do, remember this A is something like the amplitude of some oscillating function. What I'll assume is that this A prime is much less than this term and that term. Okay, so the WKB approximation mathematically is, okay, assume that this A double prime is very small. Okay, so how small it is, what it corresponds to physically, we'll get to it, okay, in a minute. But at this point, we are just going to, okay, throw away this term. As soon as I do that, okay, so these two coupled equations, then of course I have made an approximation. These things are now approximate, okay? All right, so let's see what we get out of this. Okay, so let's first look at the real part equation, you see now I have an a here and an a there. So I can just cancel these a's. So this allows me to eliminate a from the problem, and I have just a phi prime. Okay? So that says that my phi prime squared is equal to 2m e minus v. V, remember, is in general a function of x, over h bar squared. Okay? The minus signs go away. Now, what is 2m e minus v? Okay, e minus v is the kinetic energy, right? So 2m multiplied by that is, okay, kinetic energy multiplied by 2m. If you think of it as 1 over 2m, okay, p squared, this, let me just draw this over here. So if I have my v of x, for which I am trying to solve my equation, okay, I have a certain value for the energy, E. This distance here, E minus V, is the kinetic energy. And this thing I am going to call P squared over 2M. Okay, this P is no longer our quantum mechanical M, quantum mechanical momentum. Okay, it's just the classical momentum. Okay, so this P that I am writing down for the purposes of this chapter is the classical momentum. Okay, and you can see that this numerator is just P squared. Okay, so this phi prime becomes equal to plus or minus P of x over h bar. Okay? So the derivative of the phase, okay, is equal to momentum, classical momentum at any point divided by h bar. Remember, this is a function of x. Okay, so that's that function of x. All right? So we have found what phi is. Now let's go back to this equation and see what we can do with that. So I had this equation which said 2a prime phi prime plus a phi double prime is equal to 0. Okay? Now, I can write this, okay, as derivative of a squared times phi prime derivative, okay? So you see this is going to give me derivative of this, which will give me 2a times, okay, so derivative of this, let's just write this down, 2a times a prime times phi prime, derivative of the phi plus a squared phi double prime, okay? So if I set that equal to 0, you see one factor of a will cancel, and it's exactly the same equation that I have there, okay? So this equation implies that I can use this form, that a squared phi prime derivative is equal to 0. Okay, so that means this a squared phi prime is going to be just a constant. So that its derivative is 0. So a is going to be equal to c over square root of phi prime. Okay, so this approximation, okay, assuming that this term is equal to 0, enables me to solve for phi and a, okay, after that point, okay? After that approximation, everything is exact. All right, so what do I have? Let's just summarize this. Our psi of x is going to be equal to, okay, a contains the c, so I'll just put that c in here. And then, okay, let me just first write down the initial form. A of x e to the I phi of x, right? So within the WKB approximation, the reason I'm putting approximate sign here is because I am now using this WKB solution that I just derived. And I'm going to put in everything in from the solution. Now, what is phi? I have found what phi prime is, but phi is just the integral of this, right? So if I just integrate that, so let me perhaps put it over here. This just implies that my phi of x is going to be, okay, plus or minus 1 over h bar integral from some point to some other point, x, of p of x dx, okay? So that's my phi of x. So what is A? A is going to be equal to c over square root of phi prime. Okay, so phi prime is just that thing over there, right? Okay, so I'm going to get what? A square root of phi prime, which is going to be p over h bar, but I'm not going to write the h bar because I have a constant here anyway, okay? So it's just going to multiply that constant. That constant is arbitrary at this point. And then I have e to the I, okay, in general plus or minus I, integral 1 over h bar times integral of p of x dx with respect to x, okay? So that's my form. Okay, so that's my solution for psi. So given any v of x, I have a solution, okay, for my Schrödinger equation. I don't have to solve the differential equation, okay? I don't have to, okay, find the eigenvalues, etc. I can directly write this as the solution. Now, what are the problems with it? Okay, so let's just look at that. First of all, we said that this A double prime is going to be very small. What does that mean? Well, I have here an equation for A. So let's just discuss what does, okay, A double prime small mean. Okay, so this, I have this A equal to C over square root of phi prime, so it's going to be something like square root of P. Okay, what I have here. So A prime is going to be C 1/2 C P to the 3/2. One more derivative, A double prime is going to be, there's a minus sign, but now it becomes plus, 3 over 4 C P to the 5 over 2. So small A double prime means my P should be large, okay? So I need a large P, okay, for good approximation. Okay, so what does that mean? That means my solution will be good in regions where I have large momentum or large kinetic energy. So when I'm over here, solution is good. But when I approach places where E becomes approximately equal to V, then I am in trouble. Why? Because at those points, P goes to 0, right? Those are the classical turning points. Those are points where the classical momentum becomes zero, okay? So at those points, you see, when P becomes zero, A becomes very large, and second derivative of A will also be very large. Okay, so the approximation is good in some sense when I have short wavelength someplace. So you can imagine it's something like this. The particle is moving in this potential, and when it's moving in places where I have a nice large kinetic energy, it has a shorter wavelength, okay? So the psi itself is going to look like something like this, okay? It's going to have a shorter wavelength, but when it approaches these boundaries, the wavelength is going to get longer, okay? At those places, the approximation fails. So we'll have to look at those cases separately, okay? We'll have to look at those possibilities separately. Okay, so what do we have? We have this type of solution which we sort of suspect is going to be accurate if we have a, if as long as my energy is sufficiently above the potential energy. So we'll have to discuss the exceptions later on, but at this point there are a class of problems which we can attack immediately. Okay, so as an example, suppose I have a problem in which this E greater than V is satisfied all over the place. Okay, so suppose I have a box, for example, okay, from 0 to A. I have infinite potential here, infinite potential there, and in the middle I have some arbitrary potential. So that's my V of x. Okay, so we could solve this problem when this V of x was 0, okay, between A and B. But now what we are going to do is we are going to say, okay, I'm interested in energies which are sufficiently large. Okay, I don't want an energy over here because then energy becomes comparable to the potential energy. Those are places where this WKB approximation doesn't work well. So let me choose, okay, let me look at energies which are sufficiently higher above, okay, this level so that I have a sufficient amount of momentum. So my solution is then just, okay, something. So my solution for psi of x is going to be something, but it still has to obey the boundary conditions. What are the boundary conditions? It has to go to 0 at the boundaries. So I need to have this wave function going to 0, and in the middle it's going to do something. Okay, I know that it's going to oscillate faster perhaps when kinetic energy is larger, but eventually it will go to 0. So psi of x will look something like that. Okay? Now, what is my psi of x? Well, my psi of x is something, okay, which is going to look like C over square root of P. What is square root of P? Well, P is, remember, square root of, okay, so P itself is equal to square root of 2m E minus V, right? So I need one more square root, so it will be the 1/4 power. So this is going to go like 2m E minus V to the 1/4 power. Okay, so it's the A part. And then I'll get a linear combination of e to the plus I and e to the minus I type of terms. But I want the wave function to go to 0 at x equal to 0, so I can form the proper linear combination which makes that equal to 0 at x equal to 0. Right? So what do I do? Okay, if I have a function here, okay, so let's perhaps look at how this thing behaves in the exponent. It's e to the I, 1 over h bar, those are just constants. I have a p of x times dx being integrated. So in this case, I am integrating it from 0 to x. So this thing is going to be proportional to something times x. It will go to 0 and x goes to 0. Okay, so this is e to the something times x, plus or minus. So what do I do to get a function which goes to 0 when x goes to 0?
Multiply with x.
Okay, if I have something like e to the I kx and e to the minus I kx, how do I form a linear combination which goes to 0 when x goes to 0? Sine, right? I just use the sign. So I add this with the plus I to the one with the minus I. Okay, so I'm going to get here a term which looks like sine, okay, 1 over h bar. So let me put everything in properly. Keep it over here. P is equal to square root of 2m e minus v. Okay, 1 over h bar. And then I have this p of x, which is 2m e minus v. Okay, it's v of x. Integrated 0 to x dx. Okay, that's my wave function. Okay, this is my wave function within the WKB approximation. Now, this guarantees that when I put x equal to 0, this is an integral from 0 to 0. This x is, okay, dummy variable, right? It's inside the integral. You can make it an x prime if you like. So if you integrate this from 0 to 0, this term here is 0, so sine 0 is 0. So psi of x is equal to 0 and x is equal to 0. But I also want psi of a to be equal to 0. Okay? So how do I do that? This is c over, okay, 2m. Okay, remember this e is a function of x, so this is going to be v of a, but it's not too significant over here at this point. So I have something like this, a factor here. And then I have sine 1 over h bar integral 0 to a of this quantity 2m e minus v of x, okay, dx is equal to 0.
That integral must be an integer multiple of pi.
Okay, so in order to get this, this must be equal to n times pi. Or I must have integral 0 to a of 2, okay, square root of 2m e minus v of x, okay, dx must be equal to n pi times h bar. So I have to adjust this e, I have to adjust this value of e inside the integral so that I'm going to get n pi times h bar. And depending on which n I hit, that's going to give me the energy. Okay, so that's how I find the discrete energy values. Okay, so this is all there is to it. Okay, you as long as your energy is away from the potential, okay, then this is all you need to do. Okay, you have to just make sure that the boundary conditions are satisfied and you are okay. You see, we have not solved the differential equation, etc., but obviously we are doing things approximately. So let's do a even more specific example. Let's choose okay, so let's choose a certain type of potential there. Okay, so let's make our example a little bit more discrete. Suppose I have something like this. Okay, so x, this is my v of x. This is 0. This is point A. Okay, and I have infinite potential over here on the left-hand side, infinite potential on the right-hand side. But there is a certain, okay, minus V0 potential over here. Okay, so I have just put a dent into, okay, this is just the x-axis. I just put a dent into my potential, so half of the box is at minus V0. Okay. So what are my energy levels? Well, I have my equation there already. Okay, so but let's write down what psi of x is going to be. Over here, okay, so I take some value to be E. The momentum here is going to be square root of 2me, right? The momentum here, the classical momentum over here, is going to be what? Square root of 2me plus V0, right? Larger kinetic energy. That's my momentum. So what does psi of x look like? Okay, so there's the c, which I have to determine by normalization if I need to. Okay, and then I am going to have 1 over momentum, okay, this 1 over 4 power 2 me 1 over 4. Okay, and then I have sine of 1 over h bar square root of 2me. You see, in this case, in this special case, I don't have any x dependence in the integrand, dx. Okay. So this the integral until I get to this midpoint. Let's call this a over 2. Okay, so this is for x between 0 and a over 2. But what happens, so there are two possibilities. Let me just do this a little better. Okay, now what happens if x is larger than a over 2? Then I have to put the new momentum here, square root of momentum, 2m e plus v0, 1/4 power. Okay. Then I have a sine 1 over h bar. Okay, so this integral will be evaluated all the way to a over 2. So I'm going to get square root of 2me a over 2 plus rest of the integral, right? Okay, I have to integrate the full object e minus v from 0 to x. So this integral is now split up into two pieces, one from 0 to a over 2 and one from a over 2 to x. A over 2 to x, okay, again 1 over h bar, but this time 2m e minus, no, plus v0, okay, dx. All right, any questions? All right, so let me just write this one more time cleanly. Okay, so let's see, psi of x is going to be equal to two possibilities, c over 2m e 1/4 sine 1 over h bar, okay, square root of 2m e x, right, this integral, for x between 0 and a over 2, or it's equal to c over 2m e plus v0, okay, 1/4 sine 1 over h bar 2m e a over 2, so that's the integral up to a over 2. Then I have plus integral of this, okay, from a over 2 to x. Okay, so it's going to be 1 over h bar square root of 2m e plus v0 x minus a over 2, right? Integral from a over 2 to x. Yes.
Why are we also adding the integral from 0 to a over 2 in the second part?
Okay, because the integral is from 0 to x. Okay, so integral is from 0 to x, dot, dot, dot. So this we are writing at 0 to a over 2, dot, 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 plus a over 2 to x. Okay, because there's a discontinuity at a over 2.
But our x is bigger than a over 2.
Yes. Okay, if it's bigger than a over 2, then you have to integrate from 0 all the way to your x. Okay, so the integral is always from 0, okay, to x. Okay, so it starts from 0, goes over from to wherever x is. If it's less than a over 2, then of course it stops there. But if it's more than a over 2, then you have to integrate first to a over 2, then add from a over 2 to x. Okay? Yes?
What if we have a delta function potential in the middle a over 2 with energy E exactly?
Okay, delta functions will not have, okay, sizes which go all the way to, okay, delta functions are not, delta functions go to infinity, all the way to infinity, right? But the area under the delta function may do something, but, okay, so those are problems, those are problematic points, so you have to look at them carefully. You have to calculate and see what happens. So our next mission, which will be on Friday, right? So on Friday, we are going to look at cases where the potential may be something like a tunneling potential. Okay, so we are going to look at potentials like this, which will, as a special case, include delta functions and such things. Okay. All right, any questions about this? So this is for x between a over 2 and a. Okay? This is sine. SI is a different function, right? Okay. Now, we want psi of a to be equal to 0. Since we want psi a to be equal to 0, we want this thing, when x is equal to a, to be equal to n pi. Okay, so that means, okay, so this psi a equals 0 implies that I have 1 over h bar. Okay, so let's look at all these terms. 2me a over 2 plus square root of 2me plus v0. X is equal to a, so this is now a over 2, must be equal to n pi. So in fact, for each n, I have a certain energy, En. Okay, so each solution of that for each n is going to give me n pi. All right, so let's do that algebra. There's an a over 2 common, okay, an h bar common. So I can write this as square root of 2me n plus v0, okay, is equal to 2n pi h bar over a, right? So I have taken all these factors out, minus square root of 2me n. Is this correct? 2h bar over a. Okay, looks correct. So now I have to solve this for en. Okay, so this is the time when your high school algebra becomes very helpful. So we square both sides. So what do I get when I square two sides? I get 2me en minus v0, en plus v0, is equal to that thing squared, 4n squared pi squared h bar squared divided by a squared. Okay, there will be a cross term, minus 4n pi h bar over a times square root of 2me en. All right. And then the square of the last term plus 2me en. Okay, now looking at this, you see that this 2me en cancels that 2me en. And we are almost there. Okay, let me multiply by the reciprocal of this and move that to this side. Okay, so I'm going to get square root of 2me en is equal to, okay, one factor of these things go 4n pi, no, 4 goes completely, n pi h bar, please check my algebra, over a. Okay, I just multiplied by a over 4n pi h bar. I have to do this on that one also, so that comes in as a minus sign. Okay, 2mv0 times the reciprocal of this, a over 4n pi h bar. I think that's okay. Right? So now let me square both sides. so that I get 2 MEN equals, well, n squared pi squared h bar squared or a squared minus a cross term. So it's going to be 4m v0 a or 4n pi h bar times n pi h bar over a. Okay, that's the cross term. And then I have the square of this plus 4m squared v0 squared a squared over 16 n squared pi squared h bar squared. Okay, let me divide by 2m and simplify. So En is equal to 2m a squared n squared pi squared h bar squared. Can you see what this term is?
Energy levels in the quantum well.
Yes, okay, so this is the energy level of the quantum well if there is no this dip V0 present, okay? So if you like, this is like the En0, okay, the unperturbed energy. Okay, so let's see what this is. This is going to cancel a, okay, so lots of cancellations here. 4, 4, n, pi, pi, h bar, a. So you feel like there's nothing left, and you're right. There's a 2m here, so that's minus v0 over 2. So you see what we get. We get the original term, original, simple square well energy. So if you like, this is what you can call En0. That's without any perturbation. If we did first order perturbation theory, this is exactly what we would get, right? Half of the box has potential V0, so it just sort of brings it down. Okay, so this is like our En1, which we would get. Okay, if we did first order perturbation theory, it's half of the box reduces the potential by V0 over 2. If it was the full box, we would just get minus V0. But since it's half the box, we get just half of it. And then we have something here which we have to work out. So 4, and we are left with, let me just write that down, V0 squared, okay, divided by, well, let me write it separately. There's a 2m here, so that's going to be 1 over 8m n squared pi squared h bar squared. Okay, so it's going to be 1m in the numerator, 8a squared. Can you sort of see what this is? I again have n squared pi squared h bar squared over m a squared. Okay, so this En0 is h bar squared over 2m n squared pi squared over a squared. So there's an En0 hidden in it. So I think it's 1 over 16 or something like that. Okay, so it's going to be V0 squared over En0. And the factor, I think, will be something like 1 over 16. Right? Because I needed 2m here. So that makes that. Okay, so that's our final result. So you see, we obtained a solution without having to solve any differential equations or anything, okay? We have the potential, and we just integrate the potential. And when you integrate the potential from one end to the other, we get n h bar. So it's something like, okay, quantization of product of classical momentum and the, okay, so what are we obtaining here? We are getting an integral 1 over h bar p of x, if I integrate classical momentum over a path from one end of the potential to the other end of the potential. Okay, let me move this h bar to the right-hand side. I get n pi h bar. I get some sort of quantization of this p times dx. Obviously, this is approximate. This is within the WKB approximation. But you see that the integral of this quantity, which will come up in other places in physics, when you integrate it from one end to the other end of the allowed motion, this has to be some integer times h bar times pi. Okay, so this is an interesting way to quantize stuff. Okay, let's stop here. We'll continue on Friday.